Today we will discuss wave reflection and refraction at discontinuities. Study the behavior of the line to the waves when they reach the other end of the line or whenever they see a change in the impedance at its ends. Impedance other than the character impedance of the line. We will study the behavior of the reflection and refraction wave on the transmission lines. Now consider a open circuit line. First consider open circuit line or open end line. So draw the equivalent circuit first for a open end line. Consider a small section at the tail end, that dx, connecting switch S, voltage V. It's an open end line. See, when switch S is closed, a voltage and current wave of magnitude V and I respectively travels towards the open end. These waves are related by the equation V by I equals to Z, where Z is the characteristic impedance of the line. Consider the last element dx of the line, because it is here where the wave is going to see a change in the impedance. The impedance different from infinite impedance as the line is open-ended. The electromagnetic energy stored by the element dx is given by half L dx I square. The electromagnetic energy stored and the electrostatic energy stored in the element dx will equal half of c dx v square. As the inductance will be L dx and the capacitance will be c dx, as the parameters in a transmission line distributed throughout the line. So the inductance for the length dx will be L dx and the capacitance will be similarly c dx. Half c dx v square is the electrostatic energy. That will be v1 square. v1 square is the voltage at the open ended. Now if we simplify, the net electromagnetic energy will be 0. It vanishes at the open end. The current is 0. The recipient terminal is open. The current at the recipient is 0. The electromagnetic energy vanishes and is transformed into electrostatic energy. As a result, let the change in voltage be V1. You can write V1 by I square is equals to LC. You get this one, 1 by 2 L dx I square is equals to half of C dx V1 square. Again, here V1 is equals to I into Z, that is equal to V. This means the potential of the opponent is raised by voltage V volts. Therefore, the total potential at the open end when the wave reaches this end will be V plus V, 2V. The wave that starts traveling over the line when the switch S is closed could be considered the incident wave, and after the wave reaches the open end, the rise in potential V could be considered due to a wave which is reflected at the open end. Actual voltage at the open end could be considered as the refracted or transmitted wave. So we can write refracted wave equals to incident wave plus reflected wave. So you can write refracted wave is equals to incident wave plus reflected wave. We have seen that for an open-end line, a traveling wave is reflected back with positive sign and coefficient of reflection as unity. Let's see now about the current wave. As soon as the incident current wave I reaches the open end, the current at the open end is zero. The current at the open end is zero. This could be explained by saying that a current wave of I magnitude travels back over the transmission line. This means for an open-end line, a current wave is reflected with negative sign and coefficient of reflection unity. The variation of current and voltage waves can be explained. After the voltage and current waves are reflected back from the open end, there is the source end. The voltage over the line becomes twice a voltage at the sending end and the current is zero. The voltage at source end cannot be more than the source voltage V. Therefore, a voltage wave of minus V and current wave of minus I is reflected back to the line. It can be seen that after the waves traveling a distance of 4L, where L is the length of the line, they would have wiped out both the current and voltage waves, leaving the line momentarily in its original state. You can see the variation of voltage and current wave in the transmission line. Open-end transmission line. Now observe at T transmission line 4L, V and I vanishes.